Hi guys, how's it going? So today actually we're gonna be going through system design content. We're gonna be designing an e-ticket system, but in the context of soccer. So we're gonna be actually looking at English Premier League. So we're gonna think of like an e-ticket system as a system that enable users to book available seats to an event. In this case, it will be a soccer game. So what are the key things that we should keep in mind when we're building this? We expect the app to be able to show different cities where its affiliated stadiums are located. For instance, for a city here in Manchester, there are like teams like Manchester United, Manchester City. So if the user select a city like Manchester, we should be able to show them like stadium like Old Trafford, which is a stadium for Manchester United, right? So when a user select the city, we need to show them only the soccer matches in that city. Okay. So we also need to show the user who select the soccer match. We need to show them the stadium name that the match is taking place. We should also consider the user booking seats at the stadium or at the maybe shopping center. So mainly because we want to, if we don't do this, you can imagine that we will never know how many users have booked to attend a soccer game. So we want to know the users who booked not from our system, so that we can know the users who are going to attend the soccer game. Okay, if this is only if also we have some external sources where users are allowed to buy the ticket. Okay, so the app should show the seat arrangement and user can select the preferred seat. So you can think of this as from the UI on the stadium, you can see all the available seats and you can see where the seats are located and you can see the seats that are available. So which means that we need to kind of like keep track of the seats IDs. So the user should be put on hold for 5 minutes while they make a payment. So this is to make sure that, let's say it's like you can think of it like as like adding to a cart. So let's say you select the match ID and you add it to the cart. So you are reserving it. Then we give you 5 minutes to make a payment. Why are we doing this? It is because we don't want, you can imagine that let's say the two users were selecting the same match ID and the same seat ID. So the first user will make purchase, then that's the one that got the seat. But then this was going to cause a lot of confusion. So we don't want that to happen. We kind of like giving the user that 5 minutes then to we reserve that seat for them. Then they make the payment so that we avoid collusion of like multiple users purchasing the same seat. Okay, it will give a bad user experience anyway. So similarly, users should wait if there is a chance a seat can be available or cancelled. So for instance, if the user that we gave 5 minutes and they actually don't purchase that seat, then we should be able to alert the users in the waiting list that that seat is now available. We should have a function to kind of like be able to cancel the seats and do some sort of like refunds. So what are the non-functional requirements? So I'm gonna choose consistency and partition over availability. So this is because I'm gonna treat ticket booking more like a transaction. Like I want that ACID. The reason is because of this is because I want to make sure that there is only one record, one booking that is happening. So I don't want like multiple process to make two bookings. So hence here I also included that the system should be high concurrent, meaning that we should be able to expect multiple bookings for the same seat at the particular point. So we should be able to have some sort of like a mechanism to make sure that two users don't book the same seat, right? Like there's some optimization like Redis log that we can do on MySQL SQL databases or something like that. So I made some like certain assumptions, which is that there will be bots that will purchase as many tickets as possible and resell them at the higher prices, right? So we should be able to handle this, meaning that we need some sort of like a way to verify the users, you know. So traffic will spike on the popular soccer matches, especially let's say we're playing Manchester United and Liverpool or maybe Manchester City. So we should be able to keep that in mind. So let's do some sort of like system estimation load. So I'm just gonna zoom in here to show you all these teams. So this is UK, and you can see how the teams are spread across. We have Manchester City, Manchester United. Pretty much like these are all the teams, right? So what I want to do now is to like estimate the load that the system will have to handle. So we can assume that across all the cities, right, we have 20 clubs, right, distributed in less than 12 cities, right? So in English Premier League, like there's like 20 clubs, and all those clubs located in like 12 cities, right? So Manchester United has like the largest seat with like 74,310 in terms of capacity, and the smallest is the Bournemouth with 11,307 seats. So my assumption is that if English Premier League stadium always full, right? Like there's always people attending. Like most of the tickets are always sold out for every game. So I think we should then for our estimating the load, we can take an average of the stadium capacity. So meaning that for all the team seats, we're gonna take the average. So assuming that the average is, I did calculate this I think prior, so 40,000. So we're gonna say 40,000 times 20 teams, and we're gonna say times 10 matches. So there's 10 matches a week because there's 20 divided by 2, so there's gonna be 10, right? So this is gonna give us 8 million ticket sales a week. So we convert this to, it's gonna be 1.2 million ticket a day, and we can actually roughly say that we should be selling 15 tickets a second, assuming that this is evenly, which is not true in most systems, right? So because of maybe it's people like they buy a ticket at the specific time, maybe they're working in the midday, maybe they're sleeping late, so maybe they want to buy a ticket at 5. So we should like take into consideration that. So and another thing is that there might be spike at different time, so we should be able to add that into our calculations. So the storage estimate, we're gonna assume that each seat booking needs 50 bytes. So it's gonna be 1.2. We're gonna multiply it by 50 bytes. This should give us 100 megabyte. So we will be storing like 100 megabyte a day of ticket sets. Okay. So what is an API design? So we're gonna expose RPC for our microservices internally. Then for the client services, we're gonna use the REST APIs. So we're gonna have an API to search match. We're gonna take an API token occupied by the keyword that the user wants to search. It could be that they want to search Manchester. We want to make sure that we check the spelling, latitude, longitude, and radius. Then we have an API to reserve a seat. It's occupied also by an API token. We take a session ID, match ID, seat to reserve. It can book multiple seats, but maybe we should also have a maximum number of seats one user can book. So now coming to the database design, each city have multiple clubs, right? For instance, we know that London, Chelsea, Arsenal, Tottenham, right? So a soccer match is a once-off event. So I'm raising this so that you know that this is not similar to movies. So with movies can be watched at like 11, can be watched as like 12 in different rooms, right? So movies is different from soccer match, is different from a cinema. Okay, so that's all be kept into mind also. So this is how the design goes like. So we have a user, right? User ID, name, email, phone, and we have bookings, right? So a user can make multiple bookings. Maybe we have a limit, maybe not more than 5, and they can book multiple seats because maybe they're booking for a family. Um, we're gonna talk more about this status, especially when we get to like the services. But you can think of the status as it's going to help us to know if this is reserved, this is booked, this is cancelled, and we know that which match the user has booked for. And there's gonna be a booking is gonna be associated with match ID. This is gonna be a match ID which shows home, visitors, and all of these teams. So a booking, because we have number of bookings, so a booking is going to be associated with multiple. It's going to have multiple seats, and also a match ID is going to be connected to the seats. Okay, so this is just to make sure that we know that the booking that is associated, the booking, right, for this match, we know that the user want to take which seat. Okay, and we know that the match is associated with which stadium. So I included stadium so that we can have the seats for each stadium. So you can think of this table here as it stores the seats at the stadium. So I think maybe Manchester United, there's like 70,000, so capacity, so you can think we're storing 70,000 seats here. So then here we can be able to know that, okay, for this match, for this booking, this is the seat that was booked. So this will actually help us to know which seats are occupied. Yeah, you can go further, include a seat here and show the stadium is associated with which seat here. Okay, so high level design. What are the key components that we're gonna need? So we're gonna have a client and load balancer and the web server, which will be responsible for loading static pages and making requests, HTTP requests to the application server, which will be responsible for most of our business logic. We're gonna cache some of the mostly requested data, and we're gonna have our databases, right? So what is like the workflow like? So we can think of like a user is gonna search for week games, right? So a user can select a match, so that is gonna take place. A user then is shown available seats for that match. Then the user can select the number of seats. So if the seats are available, the user then has the chance to actually be able to reserve those seats. Else, maybe the seats are occupied, then they have to select the different seats. There is a point that the seats are sold out. So if the seats are sold out, then the user is taken to the waiting list because some seats are reserved. So maybe some users won't purchase them. So if that user do not purchase them, we're gonna alert them that, okay, the seat is available. Else, we're gonna send them an email, or maybe we're gonna have some sort of like a pooling to update them in real time if they're still on the app. Okay, so users that have actually reserved have 5 minutes to make payment after reserving a seat, right? So that way we can actually be able to mark their seat as complete with that transaction. I know that I'm showing a lot of text, so now let's look at the diagram, which is, I think it might be much easier for you to look into. So same thing that I spoke about, search matches. So the interesting part is when we come to reservations. So when this user comes to the reservations, what we're gonna do in the back end, we're gonna have a couple of services. So we're gonna reserve a seat, but we're gonna call this functions can seats be reserved. So if the seats can be reserved, we're gonna then call this function, which is gonna then track the reservation. Remember that they have 5 minutes, right? So this service is gonna be the one that makes sure that handle that service for us, like to make sure that okay, the user has 5 minutes to make the payment. If they haven't made a payment, we're gonna kick them out of that reservation to say maybe reservation is not complete. Then there are some users who might be in the waiting list, right? Because maybe they reserved. So we're gonna have to then push them to let them know they're waiting in the queues. We're gonna let them know that okay, they can reserve a seat, so they can do that. If there are no seats to be reserved, if there are reserved seats available, then we're gonna push the users to the queue, and they're gonna be queuing here. So we can think of this as a long waiting list for those users. Okay, so that's like high level overview. So now let's jump into more details into this active reservation service. So how does this thing work? So we want to keep all the active reservation and the ones that have expired. So the waiting service keep track of all the waiting user requests, right? So as soon as it gets a notification from the activation, so we're gonna book a seat for those users. Okay, so the key point here is that the timestamp is gonna be quite important, and latency is key because we don't want to update the database every time someone makes a requisition. This might slow down the performance extremely. So what are the optimizations that we can make then? So we can use a linked hash map whereby we store the match ID, and we in the linked hash map we store the booking ID including the timestamp. So the timestamp is that 5 minutes that we want to keep track of. Then this is going to show us the booking ID. Why are we doing this? It's because we want to make sure that we can pull the match ID and we can pull the booking ID as quickly as possible. So the client will be making reservation for different soccer matches. We can make a constant lookup in OAuth1. So we go to match ID, we go to a relevant booking ID, and if they've made a payment, it's gonna be OAuth1 lookup. So this is gonna be quick to remove them from the reservation, mark them there. So that's why we're using a linked hash map. So like I said, a linked hash map enables us to jump to any reservation and remove it when booking is complete. So a head of linked list will point to all the reservations so that the reservation can be expired. Yes. So let's say this is going to point to the older reservations so that when they are expired, we can actually be able to remove them. So then how do we persist the data in the DB? I think we had a DB here. Yeah. So we need to update the DB. So how will this one work is that this is like the workflow in terms, so the user will reserve, right? Then the status will be set to reserved, right? Then when they make a payment, right, like we said, we're gonna set them to booked. But if their 5 minutes collapse, we're gonna have to set this to expired, or we're gonna delete this record, right? Then after we've done that, we're gonna have to remove them from also the linked hash map that we created. Okay, and we're gonna remove them from there. So that's that. Now let's go to the waiting service, waiting user service. So to maintain a low latency, we keep clients in memory in a linked hash map to jump to any user we want to remove from the waiting list so that they can make any reservations. Okay. So the head of the linked list will point to the longest waiting user, so we can get them very quickly. So we're gonna have a long pooling, which can be used to keep the client on the client side to say, yeah, you can book now. There's a space for you. Okay. So when I also touch on the concurrency, so no two users should book the same seats. SQL database will be used, and I think this is a statement that you can use in SQL Server. So just to make sure that like no two user like update the single record, right? You have a single record here and it's booked, so you don't want that ID to kind of like be processed by different two processors, as much as this will be a distributed system. So I think also on the cache side of things, we can use something like Redis log to make sure that we don't read multiple IDs. Two processes don't read multiple IDs. Okay. So fault tolerance. If the reservation crashes, we can read the data from the booking tables, right? Because we have stored it in that booking table. We persisted after we have persisted in the cache. So we're gonna use the master-slave architecture. So it's commonly used, especially for SQL-based database. So it's how it enables us like to have the fault tolerance. Then we're gonna look at partitioning our data. We can partition our data on match ID. So, however, the problem with partitioning the data with this is that, especially when like we have matches like Liverpool and Manchester, then this will cause high load on the single server, because now like you have like a lot of people, everyone wanna watch this game, everyone wanna go to the stadium and watch it, so the server will be overwhelmed if we group by the match ID. So I'm personally thinking that we can have a match ID and we can have a bucket, something like that. Then this way we get to partition these requests to different bucket. I think even especially for these matches like Liverpool or maybe Manchester United, Manchester City, we can have multiple bucket for them so that we can redirect the request to different servers. Okay. So one of the things that I'll have talked about, I think I'll have actually expanded on the notification services. Especially I didn't talk about it that much. These are the things that I'd like to improve, like pooling, there's WebSocket. How do we then continuously update the user on the client? And obviously, if the user then tried, okay, there is 5 minutes, maybe there is no need for us to email them. Maybe that's another thing we should keep in mind. So maybe that's why we don't have to talk about emailing them, right? Then I would have liked to talk more on the search and how we can have optimized it, and I'll have to talk about more about the cache. There's something that I'll have liked to improve. But like any system, there's so many things that you can talk about, load balancing. So I just wanted to talk about the core aspect. I think that's what is important. And for me to show you that, I want to show you a real world use case. So this it's an article that I like so much. It's called that when Taylor Swift crashed Ticketmaster, a lesson on scaling Spike. So essentially, Ticketmaster is a ticket company in the United States, and they're the major so they had a major system failure. So I think when Taylor Swift had an event, a lot of people were supposed to buy ticket. I think they had like 14 million of sales, and they were expecting like 2 million of sales. So that's like what went wrong. So, but I want to get into like the key advices from. I like this article; it's quite good. So, so he kind of like lay out the major things that led to the failure. So, is one is high demand. So, Ticketmaster sold 2.4 million ticket compared to the 14 million customer bots trying to buy set tickets. What their post-mortem indicate that most firms invited to the pre-sale purchased three tickets on average. So they also had a DDoS attack to make the metaverse ticket had to contempt with ticket scalpers trying to purchase ticket before the verified users. Okay, so and also there's this one that we didn't actually cover in our system design, which is the retry hell. So he stated that multiple effects occurred as customer repeatedly tried to purchase ticket while they were being held in the limo with no way of knowing if their request will uh, go through or be successful. So it's like the user kept on trying, even if they didn't know. And another thing that he did raise was that essentially the user will then add their ticket, they will reserve it, then it will get expired, then they will try again. So, but one key takeaways that I like from this article is the main advices that they kind of like giving us. He says that like caching should be prioritized. The most obvious way to deal with high traffic load is to cache as much data as possible. Caching can be done at the server or client level and essentially useful for responses to frequently requested resource, right? Which makes sense. It can actually help us a lot. And I like this one. I think like this one is kind of like something unique, which is quite useful. So it's grateful discretion. So he stated that as load increases, the workflow will look something like this. So all system working normally, no request rejected. Heavy load introduce a random queuing pattern for request. Load critical randomly reject request. Sys left is reject all request. So he says that to avoid your system crashing, right? Which is what you should do is that you have these four components. So if you kind of like your system is working fine, you don't have to register any request. If you have heavy load, you start like queuing all the requests. Then a load critical, you randomly reject the request. Then system lab support to reject all requests to keep your system as safe. So I think that was quite also good. I really like that. So he said that building a waiting room and a set time to buy. So I think this is like what we spoke about now. But however, he does add that where the problem rises is when the ticket that are scattered are not actually available. So when this happens and error is still at the checkout, the user go back to the seat to put another ticket. So it's more like a cycle thing. You get rejected, then you go back. So this also add a load on the system. So it does add that also the third party dependency on the ticket master might be a problem. So the third dependencies could be MasterCard, Visa, might have caused the problem. Also, it depends on how they have actually integrated those systems. So he did mention that Ticketmaster did not actually provide a full report of what happened. Maybe we'll have actually analyze it and get into too much detail about it. But yeah, I really like it. I'll share a link with this. I think it was quite a good article overall. So anyway, thanks guys. I really appreciate you watching this.